By late August 1944, the American First and Third Armies are tearing across northern France. The greatest threat to their momentum isn't a German Tiger tank or a demolished bridge, it's physical distance. The gasoline is simply too far behind, threatening to paralyze an unstoppable army. Racing down a shattered road is a Red Ball Express truck, and rattling in the back is a single, unremarkable object, a 5-gallon metal can. 4 years earlier, this exact design was a German invention, yet the U.S. Army stockpiled nearly 12 million of them before D-Day, turning an enemy container into the most vital piece of American hardware. How exactly does a simple 5-gallon steel box dictate the speed of the most powerful mechanized force on Earth? And how did it become so absolutely critical that, by the autumn of 1944, a severe shortage of empty cans genuinely threatened to stall the entire American advance? This is not a story about a clever 3-bar handle, a perfectly welded seam, or dramatic tales of industrial espionage. It is the story of the missing link in a staggering industrial chain. You can pump millions of barrels of crude oil across oceans in massive convoys. You can build underwater pipelines across the English Channel, and you can deploy fleets of heavy tanker trucks to haul fuel across the liberated French countryside. But eventually, a single Sherman tank or a muddy Jeep is idling in a farm field miles from any depot, and a massive fuel pipeline cannot be routed directly to its gas cap. That immense, global river of high-octane gasoline had to be broken down into something small enough for one exhausted soldier to lift, carry, and pour by hand. The grand strategy of generals ultimately relied on a tiny, mass-produced object to bridge the final gap between a continent-spanning logistical network and an empty combustion engine. But to understand why this specific container became the only reliable way to keep the Allied armies moving across France, we first have to look back at the absolute packaging disaster the Allies faced at the very beginning of the war. In the vast, unforgiving expanses of North Africa in 1940 and 1941, the British Eighth Army was bleeding fuel into the sand. Their primary method for transporting gasoline to the front line was a 4 imperial-gallon tin container constructed from thin, brittle tin plate. Troops accurately and bitterly named it the flimsy. It was an absolute disaster of military procurement. The flimsy was essentially an oversized commercial oil tin, entirely unsuited for the brutal realities of mechanized combat. It was manufactured with soldered seams that simply could not withstand the violent vibrations of being transported hundreds of miles in the back of a bouncing cargo truck across the rocky Libyan desert. Worse, the extreme heat of the North African sun caused the gasoline inside to expand. The weak soldered joints would split under the internal pressure. If you stacked these tins on top of one another to maximize cargo space in a transport column, the sheer weight of the upper layers would crush the bottom rows, popping the seams and turning the floor of the truck into a highly flammable swamp. British quartermasters routinely discovered that after a long desert convoy, up to 30% of their vital fuel supply had leaked away before it ever reached a combat unit. This wasn't just a frustrating logistical waste, it was a tactical straitjacket. You cannot execute deep, sweeping, armored flanking maneuvers against Erwin Rommel's Afrika Korps if a third of your operational range evaporates into the dirt during transit. The flimsy forced British commanders to tether their operations to short, conservative distances, constantly terrified of running dry in the open desert. Across the Atlantic, the American military was grappling with its own packaging problems that severely limited operational speed. Before the United States fully committed to the conflict, Army planners largely relied on massive, standard commercial 55-gallon steel drums for bulk fuel transport, alongside an assortment of clumsy 10-gallon containers. The 55-gallon drum was incredibly durable, but it was a tactical nightmare for a frontline combat unit. A fully loaded steel drum weighs well over 400 pounds. You cannot simply hand a 400-pound steel cylinder to a single GI and tell him to go refuel a Sherman tank parked in a muddy ditch. Moving and utilizing these massive drums required heavy lifting equipment, specialized hoists, or, at the very least, several men struggling to roll them into position over uneven terrain. Once a 55-gallon drum was finally wrestled alongside a vehicle, extracting the fuel required a cumbersome hand-cranked pump or a carefully rigged gravity feed. It transformed a quick refuel into a static, labor-intensive industrial operation. In a rapid fluid battlefield, where an armored column might need to top off its tanks and immediately keep moving to exploit a breakthrough or escape incoming artillery fire, requiring a tank crew to park and wrestle with heavy machinery was dangerously slow. Furthermore, concentrating so much fuel in a single container meant that a single piece of stray shrapnel could instantly wipe out 55 gallons of precious gasoline. The American military needed a container that moved at the speed of blitzkrieg, not at the speed of a commercial rail yard. The solution already existed, and it belonged to the enemy. Anticipating the highly mobile, aggressive armored warfare that would define the early years of the conflict, the German military had recognized the critical flaw in bulk fuel transport long before the first shots were fired. They understood that armored spearheads pushing deep into hostile territory could not afford to wait for heavy, vulnerable tanker trucks to navigate destroyed infrastructure, nor could they waste time wrestling with massive industrial drums. They needed a container that bridged the gap between a supply depot and a moving panzer. The result was a masterclass in pragmatic military utility. They called it the Wehrmacht Einheitskanister, and it was a brilliant piece of stamped sheet metal engineering. Unlike the British flimsy, it was constructed from robust steel, with its two halves firmly welded together. Crucially, the weld was recessed below the protective outer edge of the container. If a soldier dropped it off the back of a moving truck onto hard pavement, the impact would strike the reinforced edge, not the vulnerable seam, preventing a catastrophic split. The flat rectangular sides allowed for incredibly tight, secure stacking in cargo beds without wasting a single inch of valuable transport space. But the true genius of the German design, the element that made it a perfect instrument for a fast-moving, mechanized army, was its three-bar handle. This single design choice revolutionized how fuel moved by human hands. If a German soldier needed to carry empty containers, he could grasp two inner handles in one hand, easily carrying 4 empties at a steady run. If the container was full of 20 liters of gasoline, weighing roughly 45 pounds, one soldier could carry it comfortably by grasping the central handle, keeping his balance perfectly centered. Most importantly, if a container needed to be moved quickly up a steep hill, across a muddy trench, or handed up to a crewman standing high on the engine deck of a panzer, 2 soldiers could grab the 2 outer handles simultaneously, sharing the load effortlessly. It allowed for incredibly fast, efficient bucket brigades, moving tons of fuel by hand in minutes. The capacity itself was a calculated tactical decision. 20 liters, or roughly 5 gallons, was the absolute sweet spot. It contained enough energy to significantly extend a vehicle's range, yet remained just light enough for a single, fatigued infantryman to lift, carry, and pour without requiring a specialized pump or a second man to help him lift it. It didn't take long for Allied soldiers to recognize they were fighting against a superior logistical tool. During the early campaigns, British troops began encountering these strange, flat-sided German containers in captured supply dumps and abandoned vehicles. They immediately realized that this object solved the exact crisis that was paralyzing their own armored units. They began hoarding them, refusing to turn them over to salvage units, strapping captured jerry cans, as they quickly dubbed them, onto their own tanks and trucks. A black market of sorts developed on the front lines, where a captured German fuel container became a highly prized possession, far more valuable than a fragile British flimsy. The British High Command eventually realized they couldn't fight a mobile war relying on captured enemy supplies. They acquired detailed specifications of the German design and began producing a near-exact replica to replace the disastrous flimsy. When the United States began coordinating its logistical strategy in Europe, American quartermasters didn't need to waste months in a laboratory attempting to invent a better fuel container from scratch. The perfect solution had already been engineered in Berlin. The challenge for the Allies wasn't to invent something completely new, but to recognize a superior enemy design and scale it to an unimaginable degree. The United States military didn't let national pride get in the way of a practical solution. They didn't try to reinvent the wheel from scratch. They did what an industrial powerhouse does best. They found what worked, adapted it to their own production lines, and scaled it up to a staggering volume. While the British essentially swallowed their pride and copied the captured German design almost exactly, meticulously reverse engineering the tight sealing lid, the American quartermasters took a slightly different path. They developed their own version, quickly dubbed the Blitz can, or later simply the American. The U.S. Army wisely retained the core physical features that made the German original so revolutionary. They kept the flat, rectangular steel body that allowed for dense, highly efficient stacking in the back of a transport truck. Most importantly, they kept the brilliant three-bar handle, recognizing that the ability to quickly pass, carry, and distribute these containers by hand was a non-negotiable requirement for a fast-moving armored force. If the structural geometry wasn't broken, the American planners weren't going to fix it, but they couldn't resist making one major alteration. And this is where the popular myth of a flawless American copy falls apart. The original German can featured a hinged, cam-locking mechanism, a brilliantly simple clamp that opened quickly and sealed incredibly tightly, preventing leaks even under severe pressure. American engineers, however, opted to replace this intricate locking mechanism with a standard, threaded screw cap. On paper, this seems like a pragmatic simplification, making the cans easier to stamp out in domestic factories that were already geared towards standard threaded closures. In the muddy reality of a combat zone, it was a noticeable downgrade. The problem wasn't just the screw cap itself, it was how the fuel actually came out of the can. The German design featured a wide mouth equipped with a breather tube that allowed soldiers to pour gasoline directly and smoothly into a vehicle's tank without needing a funnel. The American screw cap design, however, required a separate, detachable, flexible nozzle to pour the fuel cleanly. In the chaos of a forward staging area, under the pressure of a rapid advance or incoming fire, these separate flexible nozzles were constantly misplaced, crushed under truck tires, or simply left behind in the dirt. Without that crucial attachment, a soldier trying to tip 45 pounds of gasoline into a Sherman tank would end up spilling a significant portion of the precious, high-octane fuel down the side of the armor and onto his own boots. It was an irritating, ubiquitous flaw. Soldiers complained bitterly about the lost nozzles and the wasted gasoline. Yet the War Department had already made its calculation. The American might have been slightly inferior to the precise German original, but it was light years ahead of wrestling with a 400-pound steel drum in a combat zone. They accepted the flawed screw cap and pushed the button on wartime manufacturing. The industrial machinery roared to life, stamping out these slightly imperfect metal boxes at a blistering pace, committing to churning them out by the millions despite the known spilling issue. But this massive industrial commitment raises a fundamental, glaring question. By the time the Allies were preparing to invade Europe, their logistical network was already a marvel of modern engineering. They were building fleets of massive oil tankers, deploying thousands of heavy tanker trucks, and designing unprecedented underwater pipelines to pump fuel directly across the English Channel. If you have the technology to move thousands of tons of bulk gasoline through pipelines and heavy trucks efficiently, why would the Army commit precious steel and factory time to mass-producing millions of tiny, flawed, 5-gallon cans? The answer lies in a fundamental illusion of industrial warfare, the belief that bulk efficiency on a map translates to operational reality on the ground. When military planners looked at the global supply chain in 1943, they saw a masterpiece of macro-level logistics. Deep in the heart of Texas and across the American Southwest, massive refineries were churning out millions of barrels of high-octane aviation fuel and vehicle gasoline. This vital lifeblood of the Allied war machine was then pumped into the bellies of colossal, ocean-going tanker ships. These maritime behemoths, heavily escorted by destroyers to survive the U-boat wolf packs prowling the freezing waters of the North Atlantic, carried fuel by the thousands of tons. From a purely mathematical standpoint, moving liquid in a single, massive hull is the absolute pinnacle of efficiency. When those tankers finally arrived at the heavily fortified deep-water ports of Great Britain, the bulk efficiency continued. The ships pumped their liquid cargo directly into massive, camouflaged, shore-based storage tanks. From these concrete and steel reservoirs, the gasoline was channeled into extensive networks of inland pipelines, or it was pumped directly into hundreds of specialized railroad tank cars. These trains, essentially rolling pipelines, could move immense volumes of petroleum across the English countryside with mathematical precision. To a staff officer sitting in a comfortable office in London or Washington, tracing these thick black lines of supply on a wall map, the logistical problem appeared solved. The fuel was flowing, but wars are not fought on maps, and they are not fought in the sterile environments of deep-water ports or rail yards. The friction of war occurs at the tactical edge, and at the tactical edge, Bulk infrastructure is completely, utterly useless. Imagine the reality of a combat zone. An armored column has pushed forward, exploiting a gap in the enemy lines. A single M4 Sherman tank, weighing over 30 tons and burning gallons of fuel for every mile it travels, is now idling in a deeply rutted, muddy field, perhaps 20 miles away from the nearest intact road. Or consider a heavily laden 2.5-ton cargo truck, the legendary Jimmy, that has been forced off the main highway by a blown bridge or a sudden artillery barrage, now mired to its axles in a tangled French hedgerow. The engine is ticking, the crew is exhausted, and the fuel gauge is resting on empty. At that precise moment, the existence of a 10,000-ton tanker ship, safely anchored in a harbor 200 miles away, means absolutely nothing to that tank crew. The existence of a high-pressure petroleum pipeline, terminating at a railhead 40 miles to the rear, is equally meaningless. You cannot route a massive, fixed pipeline through a shifting, chaotic battlefield directly to the gas cap of a moving vehicle. You cannot drive a vulnerable, unarmored, 3,000-gallon tanker truck across cratered fields through active kill zones and expect it to arrive intact. And even if a heavy tanker truck could somehow navigate the shattered terrain to reach that isolated Sherman, concentrating that much highly flammable liquid in a single, thin-skinned vehicle right on the front line is practically begging for a catastrophic explosion from a single stray mortar round. The grand, continent-spanning river of bulk petroleum had a hard, physical limit. It could only flow so far before the geography of violence forced it to stop. This stopping point created a terrifying logistical chasm between the sprawling bulk infrastructure and the individual combustion engines that actually fought the war. To bridge this chasm, the United States Quartermaster Corps formalized a concept that became the bedrock of their operational doctrine. They called it retail distribution. The official quartermaster history of the war establishes this doctrine with absolute clarity, regardless of how gasoline reached the theater of operations, whether by ocean convoy, underwater pipeline, or railway network. The 5-gallon can was the absolutely indispensable instrument for the final retail distribution directly to the combat forces. The military recognized that to win a war of movement, the macro-level industrial supply chain had to eventually be atomized into micro-level packages that could be manipulated by human muscle. Trace this vital chain of custody visually, and the true scale of the operation reveals itself. The deep-water tanker ship arrives and disgorges its cargo into the massive, static storage tanks. The fuel is then transferred into the railroad tank cars, which thunder down the tracks until they reach the absolute edge of the secure railway network, the forward railhead. This is where the bulk efficiency abruptly dies. This location is known as the decanting point, and it was one of the most dangerous, labor-intensive, and critical nodes in the entire theater of war. Picture a desolate siding, choking on the heavy, intoxicating fumes of high-octane gasoline. Specialized petroleum distribution companies of the Quartermaster Corps work frantically in the dirt. Heavy rubber hoses branch out from the massive valves of the rail cars, connecting to specialized manifolds. And waiting beneath the spigots of these manifolds are hundreds, and soon thousands, of identical, open-mouthed, 5-gallon metal cans. Soldiers manually operate the valves, watching the volatile liquid rush into the steel boxes, constantly grounding the equipment to prevent a single spark of static electricity from incinerating the entire rail yard. As soon as a can is filled, its screw cap is tightened down, and it is immediately hauled away by a sweating GI. At this exact moment, the nature of the fuel changes. It is no longer bound by the rigid geography of rails and pipes. It has been packaged into a format that completely democratizes transport. You no longer need a highly specialized, vulnerable tanker truck to move it. Those filled cans are rapidly tossed into the wooden cargo bed of a completely standard, canvas-top supply truck. Layers stacked securely, their flat sides locking together, maximizing every cubic inch of space. This standard cargo truck, utterly indistinguishable from a truck carrying rations or ammunition, now becomes a tactical fuel asset. It grinds its gears and leaves the railhead, driving the final, treacherous miles over shattered roads, detouring through muddy fields, and navigating the chaotic debris of the front line. When the truck finally reaches the isolated tank crew, or the dispersed infantry unit, the ultimate transaction of the entire global supply chain occurs. A single soldier grabs the 3-bar handle, effortlessly lifts the 45-pound box of concentrated energy, walks the last 50 feet to the vehicle, and pours the gasoline directly into the tank. The macro-level industrial war is thus reduced to a single, easily repeatable human motion. The can is the final, irreplaceable interface between the petroleum industry and the battlefield. Because this final, desperate link in the chain was entirely dependent on these specific metal containers, the Allied forces realized they needed an inventory that defied rational comprehension. A modern mechanized army doesn't just consume fuel, it devours it at a rate that is difficult to visualize. Therefore, to ensure that the retail distribution network would never collapse, the Allies embarked on a hoarding operation of unprecedented scale in the months leading up to the invasion of Normandy. Across the southern landscape of Great Britain, hidden beneath camouflage netting in dense forests, stacked endlessly along quiet country lanes, and piled high in sprawling, open-air supply dumps, a staggering stockpile was taking shape. The Allied forces amassed a reserve of approximately 12 million 5-gallon cans. 12 million. It was a mountain of steel, dedicated entirely to the containment of liquid. If you filled that entire stockpile at once, it represented 60 million gallons of packaged gasoline, ready to be picked up by hand and carried to a combustion engine. But to assume the United States simply manufactured all 12 million of these cans in Detroit or Ohio and shipped them across the ocean would be a misunderstanding of wartime shipping constraints. Cargo space on Liberty ships was arguably the most precious commodity of the war. Shipping millions of empty metal boxes across the U-boat-infested Atlantic was a terrifying waste of volume, and shipping them full from the States introduced massive logistical bottlenecks at the ports. Instead, the creation of this astonishing stockpile was a triumph of integrated Allied industrial cooperation. While the United States did manufacture and ship a vast quantity of the cans, a massive portion of the need was supplied directly by British production. But the British didn't just rely on their own domestic factories. In a display of profound industrial synergy, American manufacturing machinery, heavy stamping presses, welding rigs, and assembly line tooling was physically shipped across the Atlantic, unloaded in England, and set up in British factories. These American-origin production lines, manned by exhausted but determined British civilian workers, operated around the clock, churning out millions of the American design right there on the island, directly adjacent to the staging areas where they would be needed most. The combined industrial might of two empires was laser-focused on reproducing an enemy container by the millions, and across the English Channel, the enemy was watching. The German High Command, relying on intelligence gathered from aerial reconnaissance flights slipping through the radar net, reports from the Abwehr espionage network, and the interception of careless radio traffic, was deeply engaged in analyzing the Allied buildup. Initially, German staff officers viewed the American logistical effort with a potent mix of professional underestimation and outright disbelief. The German military, after all, had invented the modern concept of blitzkrieg. They had rewritten the rules of operational speed in Poland, in France in 1940, and during the initial, devastating weeks of Operation Barbarossa in the Soviet Union. They knew, intimately, the friction of moving fuel. They also knew, better than anyone else on Earth, that their own fuel container design, the original Wehrmacht Einheitskanister, was mechanically superior to whatever the Allies were cobbling together. But as the intelligence reports from England continued to filter into the headquarters of the Generalquartiermeister der Heer, a cold, creeping realization began to take hold among the German logistics planners. They weren't looking at the design of the cans. They were looking at the sheer, overwhelming volume of them. The German military possessed a brilliant fuel can, but their broader logistical system was heavily fractured. Their rapid armored thrusts were constantly tethered by a supply chain that still relied shockingly heavily on horse-drawn wagons for the infantry, and a chronic, crippling lack of motorized transport for their rear echelons. They simply did not have the industrial capacity to manufacture their own brilliant invention in the quantities required to fully package their fuel supply for a prolonged, continent-wide mobile campaign. Now, German intelligence analysts were looking at an enemy that had not only recognized the brilliance of the German design, but possessed the terrifying industrial capacity to manufacture it in numbers that bordered on the absurd. 12 million cans sitting in England wasn't just a logistical statistic. It was a blaring, unavoidable statement of strategic intent. The Germans began to comprehend the implications of that stockpile. It meant the Americans were not planning a methodical, slow-paced advance. It meant they were preparing to move fuel at a speed, a flexibility, and a volume that the German logistical apparatus could never hope to match. It meant that every single American unit, from the heaviest armored division down to the smallest infantry squad with a jeep, would be fully motorized, and their fuel supply would not be tied to the vulnerable, predictable nodes of railway lines or large tanker columns. The Allies were building an invasion force where the fuel would flow like water, carried by hand, dispersed across thousands of ordinary trucks, practically immune to centralized destruction by the Luftwaffe. The Germans were looking at the industrialization of their own tactical brilliance, turned against them on a scale they could barely fathom. The tension in the months before D-Day was thus built not just on the accumulation of tanks and men, but on the sheer, almost absurd scale of a secondary system required to bridge the final gap between a massive pipeline and a single, isolated vehicle. The Allied logistical master plan rested entirely on the assumption that this vast ocean of metal containers would function exactly as designed. Yet, this colossal preparation presents a glaring, almost paradoxical question. The 5-gallon military can is, by its very definition, made of robust steel. It is explicitly engineered to be filled with gasoline, emptied into a vehicle, and then sent back to a depot to be filled again. It is not a bullet. It is not an artillery shell. It is a reusable piece of logistical hardware. If the fundamental nature of the object is that it can be used over and over again, why would military planners demand the fabrication of 12 million of them before the first soldier even stepped onto the beaches of Normandy? Why dedicate so much precious steel, factory time, and labor to build a stockpile of that staggering magnitude if you are simply going to recycle the same containers once the invasion begins? The theoretical model of military logistics assumed a perfectly closed loop. A quartermaster issues a full can to a tank crew. The crew empties it, hands the empty metal box back to the supply truck, and the cycle repeats. In a sterile planning room, a mechanized division only needs a predictable, fixed number of containers. But the friction of combat had already shattered that pristine arithmetic. When American forces ground their way across North Africa and up the mountainous spine of Italy, quartermasters learned a brutal lesson in supply chain physics. The doctrine that each vehicle simply maintained its own dedicated set of cans was a total fantasy. When a full container goes forward, it is a highly prized asset. But the moment those 5 gallons of gasoline flow into an engine, it transforms from a tactical necessity into hollow, useless cargo. In the heat of a rapid advance, tank crews do not have the time or space to carefully strap empty metal boxes back onto their hulls. A unit under fire will never halt its momentum to catalog used packaging. The empties are dropped in the dirt beside idling vehicles. They are tossed into ditches at temporary roadside dumps, scattered among rapidly shifting frontline units. Retrieving them creates an immediate logistical nightmare. To return millions of empty cans to a rear depot, commanders have to dedicate precious cargo trucks to drive directly against the chaotic, overwhelming flow of an advancing army. It clogs the exact road networks urgently needed to push fresh ammunition and reinforcements forward. Hauling thousands of cubic feet of empty air back to the rear is a catastrophic waste of transport capacity. By pure operational necessity, a theoretically reusable item effectively becomes single-use in the chaos of a fluid offensive. To guarantee a steady, uninterrupted flow of fuel moving eastward, the Army realized they could not wait for the empties to return. They had to continuously inject fresh containers into the system. Sustaining the momentum required a reserve vastly larger than just a few days of consumption. It required a massive buffer. This harsh reality of battlefield attrition was about to hit the beaches of Normandy. In the desperate early weeks of the invasion, the absolute convenience of the can initially saved the Allied foothold. But as the American forces finally broke out and began tearing across France, that exact same convenience would rapidly engineer a paralyzing crisis of its own. In the desperate initial weeks immediately following the D-Day landings, before any deep-water ports were captured or underwater pipelines could be fully established, these 5-gallon containers were the absolute lifeblood of the Allied foothold. They were rapidly unloaded from the steel decks of landing craft, stacked directly onto the sand, carried by hand across the beaches, and thrown into the back of any available vehicle to be rushed exactly where the gasoline was most desperately needed. The official Quartermaster Corps history explicitly notes that this simple container became the absolute foundation of the initial beachhead supply. But then, Operation Cobra shattered the German lines. The agonizing stalemate of the hedgerows broke, and the American First and Third Armies suddenly began a relentless, tearing race across the expanse of northern France. The speed of this advance was intoxicating, but it demanded a terrifying volume of energy. By late August, the American armies were consuming a staggering 800,000 gallons of gasoline every single day. To feed this mechanical beast, the logistical system scaled the 5-gallon can into a weapon of mass distribution. A standard 1-ton cargo trailer could hold about 50 filled cans. A 5-ton truck could carry roughly 250. A massive 10-ton semi-trailer could haul about 500 of them at once. Supply trucks would roar up to a forward distribution point, rapidly dump hundreds of filled cans into the dirt, and immediately speed back westward empty to get more, refusing to waste precious minutes waiting to collect used containers. And here, the system began to violently fracture. The very convenience that made the containers so brilliant suddenly became its operational downfall. Because they were so perfectly sized and easy to carry, they vanished. They were abandoned by advancing infantry who couldn't be bothered to carry empties. They were hoarded by liberated French locals who desperately needed them to store drinking water or scavenged fuel. They were lost in the chaotic sprawl of rapidly shifting frontline depots. The cans were disappearing exponentially faster than they were returning to the decanting points. Army planners, observing this hemorrhage, initially calculated a staggering requirement of 800,000 new replacement cans every single month just to maintain the status quo. But the attrition outpaced even their most cynical estimates. By October, quartermaster units realized they were staring at a catastrophic deficit, a shortage of roughly 3.5 million cans. The terrifying midpoint reversal had arrived. An object that had numbered 12 million just a few months prior was now in such severe deficit that the lack of empty metal was genuinely threatening to halt the entire forward distribution of fuel. The container was no longer just a convenient accessory. A shortage of empty steel boxes was quite literally starving the tanks of gas. Which forces a logical question. If the cans were disappearing, why couldn't the military simply bypass them and replace the lost packaging with heavy tanker trucks? The truth is, the military did attempt to push heavy tanker trucks forward, as the pipelines stretched deeper into France. Tankers and pipelines are undeniably far more efficient for hauling massive volumes of petroleum over long distances, and they did slowly replace packaged fuel for the bulk of the rear echelon journey. But the harsh reality of combat is defined by the last mile, and that final stretch remained completely unsolvable by massive infrastructure. A 3,000-gallon tanker simply cannot drive up to every dispersed infantry squad, every hidden Sherman tank idling in a forest, or every temporary forward supply dump. The terrain is too broken, the unarmored vehicles are too vulnerable, and the combat units are too widely scattered. Because of this tactical friction, massive bulk fuel shipments frequently reached a dead end. To bridge the gap, quartermasters were forced to halt the tankers and decant the bulk gasoline right back into 5-gallon cans near forward railheads and the extreme tips of the pipelines. By September 1944, as logistics stretched to the breaking point, the First and Third Armies were forced to do exactly this on a massive scale. This closes the central question of the entire operation. The 5-gallon container did not replace the staggering American oil infrastructure. It was the vital adapter that connected that infrastructure directly to the machine. It translated macro-level logistics into micro-level combat. As the campaign pushed toward Germany, this final link became so omnipresent that by VE Day, nearly 21 million Allied jerrycans were scattered across Europe. This wasn't just a product of American factories churning out identical copies of a German design. It was a massive, combined Allied industrial effort to saturate the front with the only packaging that actually worked under fire. The German engineering idea behind the original container brilliantly solved a real problem of mobile warfare. But the Allied victory lay in how they weaponized it. America did not win by inventing a smarter piece of steel. They won by taking a clever German tactical tool and embedding it into an industrial system of an entirely different magnitude, using it millions of times over to connect a global river of gasoline directly to a moving machine. In the end, the ultimate symbol of American logistical dominance wasn't a sprawling oil refinery or a massive cargo ship. It was a dented, mud-splattered 45-pound steel can sitting in the dirt of a shattered French roadside. Germany unquestionably invented a brilliant container for the realities of motorized warfare, creating a nearly perfect piece of tactical hardware. The decisive American distinction was never about taking the time to design a fundamentally smarter box. Their victory lay in a ruthless, uncompromising commitment to distribution. They succeeded by weaponizing an enemy idea, successfully wedging millions of these simple containers exactly into the volatile space where the massive industrial pipeline inevitably ended and the moving combat engine began.